All right, so now let's move into chapter 5, and it's entitled Equilibrium of a Rigid Body. So if a body is rigid, does that mean it has a low temperature, it's tall and slender, it's short and stubby, it will not deform when subjected to loads, or will return to the original shape after the loads are removed? Not a clicker question, but it would be. It's not going to deform when we load it. Next class, they will deform. If a body is in equilibrium, does that mean it has to be at rest? No, it can be moving with unchanging speed without accelerating. So the best answer is it's either at rest or it's not accelerating. So I already mentioned this, talk about the conditions for rigid body equilibrium. Sum of all the forces acting on the body is equal to 0. And the sum of all the moments of the forces. So sometimes they'll drop that, say sum of all the moments and couple moments. Well, sum of all the moments of the forces, those same forces, these are the same, aren't they? So if a force is acting on the body, it can make it tend to translate as well as rotate, that same force, as well as couple moments. Well, this is, there's no equivalent couple moment in the sum of the forces. These are truly just a tendency to make the object or body rotate. That's a couple moment. How do we generate it? A lot of times we think about having a pair of forces equal and opposite separated by distance d, and then the strength of that couple is the magnitude of the force times the perpendicular distance, separation distance d. All right. Well, those, some of the moments of the forces and the couple moments have to also be equal to 0. Big part of this whole class, free body diagram. Draw one. But you have to draw the free body diagram. All right. In it, you make sure include all the forces. The other instructor, when they get to dynamics, they'll complain to the statics instructor and say they can't draw the free body diagram because they leave forces off. Or they don't know how to handle the supports or constraints on the system. That's a big failure. So they'll omit some important forces. Maybe, usually they won't leave off the weight. You know, that's pretty obvious. A lot of people will remember the weight. But they'll leave off some important forces, especially in supports or reactions. And they need to include not only all the forces, but all the couple moments. Now there's a lot of supports. Look in the text. And it doesn't really do a lot of good to look at every support right away. We'll look at a few of them and then start solving some problems where the supports are used. But what's a surface with a roller? And that roller, usually just a circle like that in 2D, and you have maybe, this is our beam. Well, if you're focused on the beam, not on the floor, that roller can exert a upward force if the beam is trying to push down. But it can't exert a force in the horizontal on our beam. It will freely roll. The roller's not going to prevent it from rolling. That's frictionless roller. The other thing with the roller, though, is if the tendency of the beam was to try to lift off of the floor, guess what? The roller's not going to constrain it to pull it down. It will only stop it from being pushed into the floor. So, okay. But you could have a pin or a hinge. Well, here's our floor maybe right here. And we have our beam or some object, some body. And then we have something that goes like this. Like that. And right in here, it's pinned. Well, what does that pin support do? It prevents this beam or body from moving to the right. If it wanted to move to the right, the pin would say, no, I'm going to hold you right here. I'm going to actually have a reaction force, the constraint to hold you right there. Likewise, it could, if the beam wanted to lift up away, it could have a force or reaction to hold it right there. Here I have them both in the positive direction. Maybe if we called this point A, I would call this the unknown force on my beam in the x direction, AX. That would be an unknown reaction of that support. And then AY would be the unknown reaction. Somebody says, well, I think AY is going to hold the beam down because the beam maybe want to lift off the surface. Well, then we're going to, here I'll probably say that a number of times. You can pick on your free body diagram and need to show the assumed positive direction of these reaction supports like AX and AY. All right, fixed support. Maybe it's like this. I have a wall and I have a beam that comes out of the wall. It's cantilevered. That means that it's not going to be pulled away. It could, if this was point, let's call it C. You could have a force CX, a force CY, as well as a moment. Let's draw it like this. Get rid of this arrow here. A moment at that point C due to that fixed support. I know this may be the first time you see it's a little confusing. What we're going to do with a free body diagram is we're going to come in and cut and isolate the focus of the study from the rest of the world. And when we have to cut through a fixed support, we will replace the action of the rest of the world, like the wall, on our object, our body. And that would be introducing CX, CY, as well as that moment at that location. A roller support, very similar. Like a roller, you could have maybe rollers in a channel, and they're linked together to something that then it can have a force this way or that way, but it would move freely that way. There's others. You need to look at the book. We need to solve some problems. Yes?
When it comes with the hinge, isn't there like a certain pin that it can keep it from rotating also?
If it's a pinned hinge, no, it won't. It'll free. That's the idea here. It would freely rotate around that. Yeah. The fixed support or cantilever would be like it's welded. It would have a reaction, a moment reaction there. So our equations, when you solve two-dimensional problems, you basically have the sum of the forces in the x must equal to 0, the sum of the forces in the y, those are two directions, and then the sum of the moments about the z-axis. Well, where are you going to put it on the object? A lot of times we put it through the origin. But there's nothing special. You could put some of the moments around point B or point C of our object. These are our standard three. On the textbook, it talks about, you know what, you can have three other unique equations of equilibrium. It'd be something like the sum of the forces in x equal to 0, the sum of the moments around a particular point origin equal to 0, and the sum of the moments around another point equal to 0. That'll work. But believe me, if you're the first time through this class or you just want to get the basics, this works 99.9% of the time. And then the book also has a little bit of a discussion is you can just have three equations which are the sum of the moments around point A, the sum of the moments around point B, and the sum of the moments around point C, all those equal to 0. Really, you can bust it all down to, you can in some problems. But 99.9% of the time, go with the general sum of the forces x, sum of the forces in y, and the sum of the moments around a particular point, often the origin, equal to 0. You ready to solve a problem? A steel frame is loaded with a force in a couple moment. Well, where's our steel frame? It's right here. So it's like a skewed T. isn't it? A little bit longer on the top on the right. All right, but that's our steel frame. This could be bolted right here. These top part bolted with the bottom part are welded. What we want to do is we want to have our rigid body, and we want to select it. It takes a little practice selecting our rigid body, but we wouldn't want to cut in between and do an analysis of the top and then do an analysis of the bottom if we can get all of our questions answered by an analysis of the top and bottom as one body. And that's probably what's going to happen. Now, let's continue to read. So we look at our steel frame. It's loaded with a force. Where's our force? Right there. It's a 70 Newton force down. Are there any other force loads on this body? No. There is, though, a load of a couple moment. Where's that? Well, it's right here. That's a 30 kilonewton meter couple moment. Now, where do they show that couple moment applied? They show it applied right here. Did they give that point a name, like point A or point B or point C? Did they give this a point out here a name? No. Something that we want to remind ourselves about couple moments. Are they free vectors? Would this problem be any different if they came over here and put this and put right there a couple moment of 30 kilonewton meter right there? It'll take you a practice a few times to convince yourself, but it will not make a difference because couple moments are free vectors. That's a difficult concept. You mean you could move that couple moment all the way over here to point B as long as it's on the object? You know, it's somehow being applied to the object. It has the same effect, and the answer won't change. Okay, so that's our force and our couple moment. It is supported by a pin at A. Now we find our location A, and we look. Does that look like a pinned support at A? Yeah, okay. So when we think about that pin, is this frame could rotate and go in that position, and that support would not offer any resistance to rotation about point A. But that support would not allow that frame to either be pushed deeper into the floor or lifted off of the floor. That pin would have a lot to say about that. It actually is going to force, it will generate a force such that it would not allow it to be lifted above or pushed down into the floor. Likewise, that pin will not allow it to translate to the right or to the left. It'll have a reaction force in that pin to hold it right there. How large would that reaction force be? We're going to calculate it. We don't know right away. All right. But that's the pin. What happens if we load it so much that the pin breaks? Another class. Machine element design. Because things do break. All right. Now, and then we have a cable B to C. So here's the cable B to C. Hopefully that looks good. They give us an orientation, little similar triangle. Remember that similar triangle for that slope, that orientation of our cable? Can the cable be in tension only, or can it be in compression? It can be only in tension only. Okay. Determine the horizontal and vertical components of the reaction at pin A and the tension in cable B to C. So what I'm going to do is I'm going to pause. I want you to look at this diagram and to generate a free body diagram of something. It's pretty obvious what the free body diagram is going to be of. And then on your free body diagram, make sure and have all your forces and any forces due to constraints. One of the constraints are going to be this pin at A, probably, and this cable B to C. And then list 3 unknowns that you need to solve for. What are the 3 unknowns that you're going to solve for? All right, I'm going to pause, walk around, see what you got. TBC, which you include in the free body diagram. All right, so let me pick it up here. What we're going to do is we're going to identify our focus of the study, some body, some object, body or object, either one. So I come in here and I'm going to cut through air and I'm going to cut through that cable. When I cut through that cable, I have to think, is there some happening across that cable? Sure, it's in tension. I cut through air, cut through here. I've got to cut through that pinned reaction. I don't cut through the concrete. No. And I don't want to cut through the beam. I want to cut through the reaction, the pinned support. Then I include the couple moment and that. So this is how I'm cutting through. And so the object I would draw over here, try and draw it a little bit to scale, something like this. And I would even put in some dimensions, 6 meters, and I'd put in 2 meters, and another 2 meters, and another 2 meters. All right. And then I would put in a load, my load that was given. I could give it a name, or I could just leave it as 70 kilonewtons. The book doesn't give it a name, but you could call it F at point D or something. And then we have the couple moment, 30 kilonewton meter. And then down here at this point A, I've got a choice, and I have cut through at this point B. So what I do is I replace, because I cut, actually if you wanted to get a little more technical, I'd come right through here and I'd cut like that. Right? So I'm cutting right at B. And when I'm cutting right at B, I have a force that is the tension in the cable pulling away from B on my object, and it has this orientation provided, which is a 3, 4, 5 similar triangle. Now down here at A, I had to cut right through the support. So you can think of, well, if that pin would break, would the bottom of this frame, would it move to the left or right? You could play the game of trying to figure out which way would it want to, what way is that pin having to hold it there? And you can say, well, I think the pin is going to have to actually push in the positive X. So I introduce AX. Why A, letter A? Because it's at location A, and it's in the X direction. Why don't we call it FAX? I agree, that's perfect. You can call it FAX as well. I think the book wants to reduce the number of letters and keep things simple, so it's just AX. And that's common in a lot of the books. But it represents the magnitude of the force in the X direction due to that pin support at A. Then the same thing here, is the support going to have to push up? So those are my assumed directions. I pause, I really look at this a long time. Do I have any information that I need to put in the free body diagram, or is everything there? Did I miss anything? Look okay? Some of you had it perfectly. That's good. Go ahead and include orientation, angles, lengths, dimensions, things like that. That's important, as well as distinguishing your forces. Now, let's do this. If I'm going to solve for, I want to find the magnitude AX, the magnitude AY, as well as the tension. Those are the 3 things I want to find. 3 things, 3 unknowns. I need to have 3 equations. Where are they going to come from? My equilibrium. And then I'll have the equilibrium in the X, equilibrium in the Y, equilibrium moments about some judicious point. So if I say the equilibrium of some of the forces in the X equal to 0, what does that look like for this system? Let's write it like this. AX is completely in the positive X direction, and we're going to have the tension, but it's in the negative X direction, and I pick off that component using that similar triangle, I pick off 3/5 t, negative 3/5 t. So I have two things on this object to make it want to move, translate in the x direction. So the sum of the forces for equilibrium and the x have to equal 0. Do I have anything else, or is that the end of my equation? Does this couple moment over here contribute to the sum of the forces and the x? No. Does this 70 kilonewton load contribute? No. AY, no. I think that's it. All right, let's come over here and now let's get another equation. The equilibrium in the y direction. Sum of the forces in the y have to equal to 0. What's that equation look like? Well, we're going to have positive AY acting upward. We're going to have tension acting downward with the 4/5 component of it. And we're going to have the 70 kilonewton downward. And that's why I put the negative sign in front. And am I done, or do I have anything else? So that's equal to 0. Now, I have two sum of the forces. Now I need a sum of the moments. Well, where's my origin? You don't have to always do it at the origin. You can do the sum of the moments around a judicious point. Now, if you've done it a few times, you'll know, you'll be counting like this. You'll say, look at this equation. I have unknown, unknown. Too bad I don't have one equation with one unknown. That's my preferred. But I have two unknowns in that equation. I have an unknown and an unknown. When you really get good at it, the sum of the moments will allow you to take and knock out two unknowns. And you'll only have one unknown in one equation from the sum of the moments. So the choice is, where do I do the sum of the moments such that AX and AY don't contribute to the moment about that point? Could I do it around this point up here, or on my free body diagram right there? Well, AY wouldn't contribute a moment, would it? No, but AX would. How about over at the point B? Oh, I didn't want to erase that. If I did a sum of the moments around point B, well, both AX and AY would contribute to that equation, wouldn't they? That's not a good place to do the sum of the moments. So, for equilibrium, what point do you want to do the sum of the moments about? About point A. Because A, I have both unknown AX and AY. If I do, they both don't contribute. So the sum of the moments around point A must equal to 0. That gives us 4/5 of T acting downward at B. True? What is that moment arm distance for the 4/5 of T acting straight down? The moment arm is going to be 2 meters. True? Now, if I think about, this is point A right there, and I'm going to go ahead and pick a particular direction, meaning that this direction is positive. The counterclockwise direction is positive for my moment. Would this be a plus or a minus in front of the 4/5 T? A plus. And you thought you didn't learn anything all this semester so far. Of course you learned a lot. All right, now let's pick off the 3/5 T, right? So it's like we separated this in the 4/5 and 3/5 T, applied at point B. And what is the moment arm distance for that 3/5 T? 6 meters. Excellent. And will that give it a positive sense of rotation around point A or a negative sense of rotation? Positive. That's right. All right. How about this 70 kilonewton load? What is its moment arm? 2 meters around point A. And will it give it a positive or negative sense of rotation? negative sense of rotation. And what about that 30 kilonewton meter? Couple moment. And that's going to be a negative 30 kilonewton meter. True? And that has to sum equal to 0. Sorry, I ran out of room a little bit there. But why did I put a negative sign? Why? There's a positive right here, but look at, they show you the direction of rotation. That's a negative sense of direction of rotation if I'm going to pick the counterclockwise to be positive. All right, now I look at this and I say, oh, this is great. T is the only unknown. And so what we could do is solve for T. And T comes in at 32.7 kilonewton. What I'm going to do is I'm going to pause and tell a few of you double check my work with your calculator. I see some of you are already going at it. That's great. Thank you. You got it? 32. So we solve for one of our unknowns. Now we go back and we can take either this x equation, that's fine, you can do that one, and you can then solve for ax. Ax is 3/5 t. It comes in at 19.6 kilonewton, box that. And then likewise, we now can come up here and solve for ay. And ay comes in at a whopping 96.2 kilonewtons. Let me ask a few of you to verify those last two numbers, okay? You got them? Both? Perfect. So let's pause, reflect on what we did. We isolated an object for analysis. We had all of our forces, all of our couple moments that were applied, and then we had our reactions. Here we only had to cut through this cable and cut through this pin connection, and we had our reactions. We have three equations in 2D. We had three unknowns. Solve for them. One of the key things you'll get good at is you'll look at doing some of the moments first, because usually that's one way to eliminate and get one equation with one unknown. But you have to solve a few problems yourself before this is realized. We have airplane nose wheel, and it's when the system is braking, there's some braking going on. There are forces that are applied to the landing gear, and it's shown as a 3 kilonewton in the horizontal and a 9 kilonewton upward. I guess the brake really doesn't help with the 9 kilonewton, but definitely helps with the 3 kilonewton load, right? So this is our model, and our landing gear must be this component. Is that our landing gear? Something like that. It didn't clearly identify what exactly is the landing gear, but there's our landing gear, okay? And this must be the part of the aircraft, right? So, determine the horizontal and vertical components of the reaction at pin C. Well, we go look. There's C, and it's pinned right there at C. Hopefully that's obvious that it's pinned at C. And the force in the strut AB. Okay, so here is location A, here is location B. They call this member a strut, S-T-R-U-T. All right, what's interesting or particular about a strut? It's either a 2-force or a 3-force member. It's a 2-force member. So when you first see these things, you want to analyze them. So let's do this. Let's cut the strut free and do a free body diagram only of the strut. Only of the strut. True? So if we cut through the pin at B and the pin at A, and we isolate over here, all right, that's a bad looking isolated object of my strut, but there it is. There is B and there is A. Okay, there's A and there's B. You could then draw the free body diagram. A lot of students would go look at, I don't know the direction, so I'm going to assume positive BX and positive BY, and I'm going to assume positive AX and positive AY. That's true. You could do that. And then you would look at it, you'd say, there's 4 unknowns. But if you did a little analysis, what do you know about the difference that when you did the sum of the forces in X, you would conclude that AX is equal to B, AX plus BX is equal to 0. True? So it's like I just went from 4 unknowns to 3 unknowns. And likewise, some of the forces in the Y, that AY plus BY is equal to, really there's not 4 unknowns for this free body diagram. They're just 2 unknowns. I'm not going to be able to solve for them. Another way to redraw this free body diagram is you could take a look at point, and you could say, look, I'm going to talk about the magnitude of the force and the orientation theta B. So my unknowns would be B, the magnitude of the force B, and the orientation theta B. See that? All right. Likewise, I could come down here and I could say this is point A. I'm going to talk about the magnitude of B, magnitude of A. And then I'm going to also talk about the orientation theta of A. These are 2 equivalent ways of drawing a free body diagram for the strut. It's just whether you choose to put the pinned reaction, AX and AY, or A, the magnitude, with the orientation theta A. They're the same way of describing the support. Now, okay, well, think about this for a minute. And if this is the way you're going to analyze it, what do you think about the sum of the moments on this object, this strut? They have to be equal to 0. True. So what is going to be the restriction here? What's going to be the... Could I really have A and B drawn like that? What you conclude is that for a two-force member, that basically the force either is going to be in tension in the object, and if they have the same orientation, they can't be anything else. So for a two-force member that's pinned on both ends, not cantilevered on both ends or anything like that, or cantilevered and pinned, but a two-force member that's only pinned on both ends is either in tension or compression, and the tension or compression is along the line of action between the two pieces where it's pinned at A and B. Now, somebody says, I'm a very clever person and I want to have a strut that is shaped like a boomerang. It's not a straight strut. Well, I don't know, because maybe the landing gear has to fold in, and I need it to, when it folds up, it needs to be bent that way so it doesn't interfere with some other component. All right, if it was a boomerang shaped strut and it was still pinned at B and pinned at A, would it still be a two-force member? Yeah. And guess what? It would still be in either tension or compression along the line of action or axis going between A and B. So even the curvature, it doesn't have to be a straight strut. Almost all struts are straight, but hey. Okay? All right. So there's our discussion of a two-force member and how it applies here. So I'm going to erase all this. And I'm going to come back and we're going to say, that's why they talk about a single force in the strut as an unknown. So the things that I want to solve for are going to be this Cx and Cy, and I'm going to call it just the force in the strut. I guess I could put F strut or something like that. If you like long subscripts, that's great. I do too. Or just something short. All right. Well, to analyze and get these three, to solve for these three unknowns, I have to get a free body diagram. And what is my choice for the analysis? I see there's two contenders for this problem. The first contender would be, I would cut through, let me do it in red. I'd come down and I'd cut through this pinned support right here where I already know the load of 3 kilonewton and 9 kilonewton are happening onto that landing gear. All right. So I don't include the tire. I cut through air. I cut through B, and then I cut through C. That's one of my choices. That choice will work. But there's another choice. There's another choice. And that other choice, I'm going to still cut down here, but I'm going to cut through A and then C. You say, that'll work too. Well, you just have to pick one and go for it, okay? So which one? The simpler one probably is just a straight object like this. And we have down here at point, what was the name of that one? That didn't have a name, but it just had a load of 3 kilonewton and a load of 9 kilonewton. Okay. And then up here at point A, it doesn't have AX and AY because it's a two-force member. A to B is a two-force member. Hence, what I'm going to do is I'm going to say, do you think it's in tension or compression, this two-force member right here? All right, we got to cut one tension. That two-force member, A to B, is it in tension or compression under this load? The braking load, it's got the 3 kilonewtons pushing back. Compression. I got a compression. Let's go around the room. Maybe you can, everybody has to raise their hand until they give me the answer and then they can lower it. So that way I vote. Which one did you go for? Compression. What you went for compression? 2 compressions. Compression. We're getting on a bandwagon here. We're compression. All right. So if it's compression, then you probably want to draw it something like this, right? That would be the right direction. F. This, maybe I'll get rid of the subscript, just call it F for the strut compression magnitude. Okay. And then I come up here and then I have this point C. Here is CX and CY. So I've chosen for my object to only have that straight section of the strut. If you wanted, somebody else could have this for the analysis. It would be just as good. And they would have over here CX, CY, F, and 3 kilonewton and 9 kilonewton. That would work as well. But you don't need to have 2 of them, right? You just need 1 for a good free body diagram. Okay? So this one we will not use, but it could be used. So let me just erase it. All right, I pause for a second. I want to go ahead and put in some dimensions and angles to help me. This right here to that is how many degrees? 20 degrees. This to that, No, this to that is 30 degrees, isn't it? So what is this angle right here? This angle, the axis and the vertical. That's my 20 degrees, isn't it? Okay, I'm just trying to get some angles on here. And then we have some lengths. You can put them off to the side from this point to that point, 0.7 meters. And then from this point to that point, 0.4 meter. Did I get those right? The lengths? All right. Some of the forces in the X, some of the forces in the Y, some of the moments around a judicious point, and let's solve for the three unknowns. All right? So I'm going to pause, walk around, see what you get. Well, can I pick it up here? Let's see what we do. I'm going to go back to this illustration and know that we had this force here, F, because I think I can maybe help with the clarity a little bit here on this. If I could decompose that force into a component that was straight down the strut, right? And then perpendicular to, you know what? I think I love these 90-degree angles. I love these little triangles. What are those triangles called? Right triangles. Didn't we say that we're going to be experts at right triangles? Because if I can decompose it into these two forces, this component and that component, one of them exerts a moment around point C and one of them doesn't. True? So this component going straight down of F, that doesn't contribute to the moments around point C, but this one does right here. So maybe you think about that as that same component there, right? Okay. So with this right triangle, I'm trying to do this. I'm trying to do the sum of the moments around point C equal to 0. Okay. What is this magnitude? It's F times the sine of this angle theta right there, isn't it? Okay. What is that angle right there? 30 degrees? It's 30 degrees. All right. Then I know that it's applied, so I really need to conceptually move it back to part A right here. But we got that magnitude, F times the sine of 30 degrees. Now, what is the moment arm distance? Is it the distance from point C to point A? Is it that distance? Yeah, okay. Is that distance 40 centimeters? No. It's close to it, but it's not precisely 40 centimeters, is it? So I look for another right triangle. So I come over here and I go straight down. There's another right triangle. But I know that this edge of this one is, if I can draw it like this, is 40 centimeters. And I'm looking for this hypotenuse right here. The hypotenuse. And so, man, let me try and think which way is the best way. Either I work with this angle or that angle. I had to pick one, right? Let's work with, get rid of this angle, this one down here. So what is this angle right there? Isn't that 20 degrees? I got a few confirmations that this angle right there is 20 degrees. Look good? All right. So what is H? Is it equal to 40 centimeters divided by cosine of 20 degrees? Yes? Yeah. All right. Why did I work so hard to get H? Because isn't that let's put 0.40 meters divided by cosine of 20 degrees. Isn't that my moment arm? Perpendicular distance, moment arm. Okay, so that gives me the contribution to this strut force around point C. True? All right, does the 3 kilonewtons, I should have also gotten the direction. If we're going to go as this is a positive direction, does that contribute a negative or a positive sense of rotation around point C? Negative, negative. Okay. Now let's go and talk about the 3 kilonewton. So we have a 3 kilonewton, and it's going to contribute a positive sense of rotation. I'll put the sign in right away around point C. That's counterclockwise. And then I need that moment arm distance. Well, what's that moment arm distance for the 3 kilonewton force? Anywhere along the line of action, perpendicular distance, what is it? 1.1 meter, true? 1.1 meter, add that 70 centimeters and 40 centimeters, okay. And then what about this 9 kilonewton? I know I should go back here to this free body diagram, but this illustration is a little cleaner. All right, so that's going to contribute negative 9 kilonewton times what? What's that moment arm distance? It's this distance right there. Well, I just make a little triangle maybe on the side, and I say that angle, yeah, right there is 20 degrees. And this edge is 1.1. So what is this distance D right there? Is the tangent of 20 times 1.1, right? Okay, so I need to stuff that in there. 1.1 meters, I never leave enough room. I'm going to scoot that over just a little bit. Times the tangent of 20 equal to 0. Now, if I did that, sum of the moments around point C equal to 0 equation correctly, then how many unknowns do I have in it? Only F. How about you solve for F? So when you run the number, you'll get that F is a negative 1.425 kilonewton. And a lot of you were shy thinking, hey, we just talked about that strut is probably in compression. Something's wrong because with the negative sign, it's not in compression, it's in tension. Now, how does that make sense? Well, do me a favor, do this. If you're not braking, if the wheel isn't braking at all, there's no brake applied, right? What happens either to the 9 kilonewton or the 3 kilonewton? Which one of those would logically go to 0? The 3. All right, let's let it go to 0. Now, if you looked at this assembly, what do you think about that strut? Does it look like it's going to be in tension or compression to hold everything in place? Doesn't it look like, oh, it's going to be in tension, right? Okay, well, apply a little bit of brake, maybe 0.01 kilonewton. What do you think? It's probably not enough braking to really switch it. It's probably still in tension. All right, 0.1 kilonewton brake. And then you just sort of creep up. I think if you broke to like 25 kilonewton, well, guess what? You probably switched it, and that strut now is in compression. But with a light amount of braking or no braking, it's in tension. That's the way I would explain it to you, or try to explain it to you. Okay? So, but this is, when you run the numbers and you do the math correctly, the signs will work itself out. Now, first time through, student says, oh no, F is negative. I'm going to go quickly and correct my free body diagram. Don't do it. You'll be tempted. I remember when I was in statics, I was so tempted. Oh, now I'm going to go change my free body diagram. Well, then you're going to have to redo all your equations. And don't do that. Get your free body diagram and sort of seal it and just stay with it. And if some of your A's and B's and C's and F's come out negative, that means it's in the opposite direction of the assumed positive direction of that force or component of that force in my free body diagram. Okay? Okay. Let's continue on. How am I going to solve for Cx and Cy? That's a pretty easy. The hard one was for the force. But you would do the sum of the forces, and the x must equal to 0. And when you do that, you get that Cx is equal to negative 4.09 kilonewton. And because I'm running out of room, I'm sure you can chase that math down. You do the sum of the forces and the y equal to 0, allows you to solve for Cy. And it's negative 9.92 kilonewton. So it's like every one of my assumed directions was not wrong, but it was the actual reaction is in the opposite direction. Which, when I look at Cy, look at it, the pin isn't lifting the strut, it's going to have to push down on the strut. So that makes sense that Cy is negative 9.92 kilonewtons. All right, any comments on that problem? A member is pinned at A, so here's the A, it's pinned. Has a smooth slot, so this is our slot right here, and has a fixed peg B or pin B that's in the middle of that slot. But that slot in my member, if the member wanted to move in that direction or that direction, the pin wouldn't stop it. But if the member wanted to move in this direction or that, the pin would stop it, right? That's what they're showing you with this slot, this smooth slot. All right, and it has a cable attached at C, and the cable has its orientation shown. And the magnitude of the force, tension force in the cable is shown, 800 Newton. Determine the horizontal and vertical components of the reaction at pin A. Well, they're asked, what are we asked to find? We're asked to find something like AX and AY, two components of my reaction support, the horizontal and vertical component of the reaction at pin A. So we would draw a free body diagram. We would have something happening because of that pin at B. We'd have up here at C, we'd have a tension force of 800 newtons with the orientation of 30 degrees. We'd have our dimension 0.7 meter, 0.7 meter. And down here at A, unless you're good at it, I would just say, look, that's my direction AX, and this is my assumed direction AY. And I could get a negative answer for either one of those. Okay, and what about what's happening at B? Well, you don't put BX and BY. That's no good. All you do is put that, is do this and put B there as an unknown. Because like I mentioned, it won't resist anything sliding in the slot, the pin sliding in the slot. But it's only perpendicular to the axis, 90 degree. All right, so if I want to find this AX and AY, how would I do it? First of all, why didn't they ask me to find for also B? Isn't that an unknown as well? Sure. So in 2D I could get 3 equations. They only asked me to solve for 2 unknowns, but B is an obvious unknown in my free body diagram. So here's a strategy. Solve for B even though they didn't ask to solve for it. And then go back and solve for AX and AY. So if you did the sum of the moments around point A, that equal to 0 for equilibrium, you can solve for B right away. Can you see what that is? It would be B times a perpendicular distance 0.7 meter. That would give a positive sense of rotation around point A. And then what do you have to do is you can decompose this 800 into this and that. Okay. Let me try to do this. This was a 30-degree angle, so this is 30 degrees right there. Guess what that angle is right there? 30 degrees. There's a lot of little angles in your mind you're going to have to work through. And this then is 800 newtons times the cosine of 30 degrees. Okay. All right. And that perpendicular distance, so let me do this one. That's going to be negative 800 newtons times cosine of 30 degrees times a perpendicular distance of 1.4 meter, 0.7 and 0.7. All right, did I leave anything off? The sum of the moments, is that equal to 0? Then we solve for B. The B is 1386 Newton. Then you do the sum of the forces in the X equal to 0. And you can solve for AX. Lo and behold, it comes out to 0. Sum of the forces in the Y equal to 0. And it comes out AY is negative 800 Newton. Those are the 2 things we were asked to solve for. This member has only a force at B, a force at A, and a force at C. This is a 3-force member. And when you get good at looking and identifying 2-force members, you'll look for them because you'll know they're either just, tension or compression along the line of the pin connections on the ends. But 3-force members are a little different. Let me see if I have another way. Yeah, what I did was I tried to blow up that illustration a little bit. And what I have is I have a line of action that goes through point B. That force that's applied to the member at B must be along that line. I have also a line of action for the 800 Newton load applied at the end. And we just calculated what the reaction is. It's AX is 0 and AY is negative 800 newtons. So along that line of action of AY, and guess what happens? Your 3-force member, it has a concurrent force system. What? What do you mean by this concurrent force system? What does that word mean? Has it been introduced in our textbook in our class before this semester already? Yeah, it did. It has been. What does it mean? All the forces happen at the same time, in the same time zone, at the same instant in time? No. Concurrent meaning they all go through the same point. All the lines of action go through the same point. So what you could have done to solve this problem is you could have made that observation. Now, maybe it's not that easy to make that observation, but that, oh, it's a three-force member. They're going to be either all three forces are parallel, that's another problem we'll solve, or they're concurrent force system. Okay. So if I go back and I look at this point right here, it's as if I have an 800 Newton force translated back there, a B load that I know we solved for it, but if I was solving this problem first, trying to make observation it's a three-force member, then it would be unknown reaction B, and then I would know that A is either down or up. And if I look at it from this diagram, it has to be down. It's pretty obvious. Because the sum of the forces at this point, what point do you want to call it? I don't know, new name of that point. Point O or point D or something. Give it a point D. The sum of those forces have to be equal to 0. And so then you say to yourself, well, then AX is equal to 0, obvious by inspection. And then what about the AY? I guess you still have to solve for B, because you would do the sum of the forces at the point D in the X direction equal to 0. That would give us that B times the cosine of 60 degrees. You have to work a little bit on this 60 degrees. How do we get that angle is 60? Well, from this one, that's 30, that's 30, that's 30. This is 30, that's 60. Oh, that's right. This right here is 30. This is 30. That means that's 30. That means that's 60. So then I get the component B in the X using either the cosine of 60. Why didn't I just do the sine of 30? A lot easier now that I look at it. Equal to the 800 times the cosine of 30. This angle right there, 30. That way you get B right away. And then you solve for A. You get the same magnitude of A. AY is the downward 800 newtons. So the same theme in 3D is you need to have a free body diagram, show all the forces. Don't forget the weight if it's there. Reactions at the supports, and the supports are more complicated in 3D because they can have some moment reaction. All right. And then any couple moments. A couple supports. I'm not going to show them all. The textbook has a great table organizing them. But what's a smooth surface support? So if I have something coming down and it touches a smooth surface, this is my object right there. The smooth surface will only provide a perpendicular or a normal reaction to the surface, nothing tangential. It's smooth, it can slide along. All right, now if it's also a surface, it can only stop it from embedding itself deeper into the surface. It will not stop it from lifting off of the surface. How about a ball and socket? Well, this one's a little harder to draw, but what you have is something, that ball inside of a socket, it could stop, and let me try and draw a coordinate system, from pulling in the X, in the Y, or the Z. It'll stop, restrain it in all three of those. So you could have a reaction support there, AX, AY, AZ. This could, it's hard to draw it, but it could rotate that object this way and that way. Okay? Okay. Pin, just like we had in 2D, but with the pin, you can also think of a hinge. So if I have an object right here is a hinge, it's plate going up on this side and a plate going on that side. That hinge is going to stop it from shifting that way, that way, that way. It'll actually stop the rotation around that axis, but not around the axis which the hinge is made to rotate. So there is going to be no resistance or moment due to that support along the axis aligned with the hinge. All right. Let's take a look at this problem.